All right, now we're going to take a look at infinite series under 15 minutes and see if that's possible. So the first thing we want to talk about infinite series is the convergence, and then we'll talk about test of convergence and ratio, root test, and absolute and conditional convergence. So we know a series is denoted by a summation of all the sequences. So the first definition that I'm going to do right here is, suppose that we have sequence where n goes from p to infinity, and suppose it's a sequence of real numbers. We say that the series, so if that's the sequence, then the series, where we denote it by summation, where k goes from some number p to infinity, for ak, we say that converges to s, some real value s, if and only if the sequence of partial sum, and we're going to call the partial sum capital S, denoted by, so sequence Sn, so Sn, where n goes from p to infinity, converges to S. So the idea is the series converges to the same value of the partial sum. So if the series converges to S, then S is called the sum of the series, and we can simply say that the summation of A sub k is basically S. That's it. It's as simple as that. Alright, so now let's go to theorem. Of course, this chapters and this section is all about theorems and definitions, no examples. So let's take a look at the first theorem. The theorem says, if we are given that the series converges, so we'll decide where is the series converging. Okay, I don't know why that is a line. I'm not supposed to have a line. Okay, so suppose we have a series that converges. Then the limit of an is 0 as n approaches infinity, and this is a theorem from calculus 2. So that is, if summation of a converges, then the sequence an, so in other words, what it means is the sequence a sub n, it converges to 0. In other words, the limit is equals to 0. Okay, the next theorem we're going to take a look at is divergence test. So this is just the convergence nth term test. The other one, divergence test, is suppose you have a sequence and it does not converge to 0, then you will say that the series diverges. So mathematically, how I can write this, so if the limit of an is not 0, so if I go ahead and find the limit, this implies that the series ak diverges. So that's another way of saying what this theorem actually means. Alright, the next one we want to take a look is another theorem. So suppose, so theorem will always have, suppose a lot of things are happening, and I keep getting a line here for no reason. Alright, so suppose we have, if a is a non-zero real number, so we have a theorem. So suppose we have a real number, so I'm going to call it a, small a, non-zero real number, which means it's greater than 0 or plus. Then the geometric series of summation AR to the power of K, where K goes from 0 to infinity, is often, or says that it has the following properties, where we will say that the summation of AR to the power of K is equal. So this is the solution. So this is, in other words, is the sum value. A over 1 minus R if R absolute value is less than 1. And you would say it diverges if R is greater or equals than 1. This is directly just applying the properties of geometric series. Alright, let's take a look at the next theorem. It's going to be Cauchy criterion theorem. So let's take a look at what Mr. Cauchy means by Cauchy criterion theorem. So the theorem is called Cauchy criterion theorem. So Cauchy criterion theorem says, so suppose you have an infinite series, so I'm going to write it A sub k, and it converges. This can only happen if and only if for all epsilon greater than 0, there exists a capital N, so some integer n, such that if n, that's a small n, is greater than m, which is greater than the n that I picked. So what it means is if I have a cap n, and usually we go by a little n, but I have an m after that, so in between with these two numbers that I picked, then Cauchy criterion says that the absolute value of the summation of AK, which means where k goes from m to what I pick to infinity, is less than epsilon. So another way, it's an absolute value of am plus 1 all the way up to an. Oh, sorry, it's not infinity, n. So between n and m, we have that it's less than absolute value, and this is what it means to be Cauchy criterion, or Cauchy criterion theorem. Okay, so finally the corollary. Let's take a look at a corollary or another idea. So in math, corollary is something you can use in your theorem, or something that emerged from any theorem. Is if a series and its absolute value, which means it's all positive, if the series, the absolute value converges, of course that AK converges because it makes sense, right? Because all series converges to the same value. All right, the next theorem we're going to take a look is integral test. So theorem is called integral test, and in order to do integral test, of course we will be given a sequence, and we're going to rewrite the sequence as a function. So our function has to go from 1 to infinity, mapping to any real number, and it's continuous, right? I mean, it has to be defined, and then it's positive, and it's increasing. So you have to take care of all these things. It must be positive, it must be increasing, it must be continuous, and then we can rewrite the function or the sequence as a function. So we will say that let's write f of k as the sequence itself for all k in n. Then we will say that the series itself converges if these things happen. So if and only if the integral, because this integral test that goes from 1 to infinity of that function dx diverges. So here we're going to use improper limit properties. Absolutely. All right, let's take a look at the next cool item right here. So the next item we're going to take a look is another theorem, and we all definitely know this theorem. The theorem is called comparison. So comparison test, it's a test. So suppose we have series A sub k and series B sub k, where B sub k is always 0, positive for all k in n. Then we're going to say we have two outcomes here. If B, that means the series BK converges, and AK is less or equals than some constant times BK, then the series absolute value AK converges. In other words, by the corollary above earlier, AK converges as well. But if the series B diverges, so here you need to make sure A, when you compare A with B, A has to be less than B. That's the key. We don't care what the constant is. So if B diverges, so in this case, A is always positive in this case, is greater than BK, the one that we are comparing, then the summation of A sub k, the absolute value, diverges. Okay, so that's the theorem of comparison test. Similarly, limit comparison is you're just going to get an idea. Remember, limit comparison, you're going to compare the limit of A sub n over B sub n, in this case where BK is not 0, then A converges. So in this case, you will say AN converges. Okay, so but if you did BN is over A and B still is, if it is BK diverges, then it diverges. In this case, we will say BK converges. So AN converges if BN converges. So that makes sense, right? All right. And finally, it's what we're going to take a look in this section is called Cauchy condensation theorem. So let's take a look at theorem Cauchy condensation test. So Cauchy condensation test is if you have a sequence, a non-negative, and if you have AN greater or equals AN plus 1, right? Then you will say that A sub n converges if and only if. So if you have the summation of 2 to the power of k times A sub 2 to the power of k. So this is what you want to do. Then we can say that A sub k converges. So all you have to do is convert n to 2 to the k, and then you multiply by 2 to the k. So if you're going to use this, you need to know the name of the theorem. It's called Cauchy condensation theorem. So the next video we'll be talking about ratio, root, absolute condition test.